Welcome back to Edulexis. Have you ever written a Python script that processed a massive dataset or a giant log file and suddenly crashed your computer with a memory error? Today, we are solving that exact problem. Standard functions use the return keyword. When a function returns a list, Python loads every single item into RAM all at once. If you have 10 million items, that takes gigabytes of memory. But what if you could generate items one by one, on the fly? That is where generators come in. Instead of return, we use the magical yield keyword. A generator is a special type of function that returns an iterator, an object we can loop over, but one that produces values on demand without storing them all in memory. Let's write our very first generator function. We'll create a simple counter. Let's call it count_up_ to n. Inside, we use a while loop, and instead of appending to a list and returning it, we write yield current. Let's switch to the code editor and see how it looks. Here is the code: def count_up_ to max_val count equals 1 while count less than equals max_val yield count. Count plus equals 1. Notice how simple that is. No list initialization, no append method. Now, let's call counter equals count_up_ to 5. Notice that when we call the function, the code inside doesn't run yet. It just returns a generator object. To get values, we loop through it using a for num in counter, print num. What actually happens under the hood when Python hits yield? Unlike return, which destroys the function's local state and exits completely, yield pauses the function, saves its entire state, and sends the value back to the caller. When the caller asks for the next value using Python's built-in next function, the generator wakes up right where it left off, continues executing until the next yield or function termination, and pauses again. Let's demonstrate this with manual next calls. What happens when there are no more values to yield? Python automatically raises a stop iteration exception, which is how for loops know when to safely terminate. You rarely need to catch this manually, but it's crucial to understand how iteration protocol works. Now, let's prove the memory efficiency claim. We'll use Python's built-in system.getSize of function to compare a list containing 1 million integers versus a generator expression producing 1 million integers. Look at this. Our list takes nearly 8 megabytes of RAM instantly. But our generator object takes less than 200 bytes regardless of whether it generates 1 million or 1 trillion numbers. That is the astonishing power of lazy evaluation. You don't always need to write a full function with a definite keyword. Python supports generator expressions, which look just like list comprehensions, but use parentheses instead of square brackets. Let's look at a real-world scenario. Imagine processing a 50 gigabyte server log file. If you use f.readlines, your RAM will instantly explode. Instead, we can write a generator function that yields lines one by one as it reads the file. Here is how clean that looks: def read_large_file, file_path with open, file_path, r, as file, for line in file, yield line.strip. This allows you to process files gigabytes larger than your total RAM safely. To wrap up, use generators when working with massive datasets, infinite sequences, or streaming data to keep your memory usage flat and efficient. If you found this lesson helpful, hit that subscribe button, leave your questions in the comments, and I'll see you in day 54.
Thank you for watching. Like if you learned something, share with your circle, and subscribe for more.